Welcome to another of my presentations on restoration and creation of clocks. This time I will take you back to the very beginnings of mechanical clockwork and explain how I believe mechanical clocks came into existence. It's hard to believe that way back in the 11th and 12th century that anybody would have been concerned at all about what the time was at night. You were just sleeping. But certain people, monasteries for instance, needed to know what the hour was throughout the night. And these devices here explain the simplicity of reckoning the hour during the night. Calibrated candles and calibrated oil reservoirs. The life of monks in monasteries in Europe were regulated very precisely, and it was the responsibility of one monk, the warden, who had to ring the bell in the monastery to awake all of the monks or bring them all to prayers every 3 hours. The little ditty down the bottom here, Frère Jacques, we've all heard before. Brother James, are you sleeping? Sound the matins, sound the matins. You can see matins as 3 a.m. He's obviously slept through. Now he's going to be in trouble because he didn't ring the main bell, so all the monks missed the prayers. What are they going to do with Brother James? Somewhere in an Italian monastery, there was one monk who decided that the candle and the oil lamp was not good enough. And being mechanically inclined, he started to work on a device, a mechanical device, that would wake him up and prevent him from oversleeping. Clocks had been in existence 1200 into the 1300s, but there is no pictorial reference to any mechanical clock in any documents up until 1364, when Giovanni Dondi published his treatise on a mechanical alarm or alarum. And here is the original document pictorial reference. Here is a painting by Sandro Botticelli of St. Augustine at work in his study. And behind him on the shelf is an alarum, a 24-hour rotating dial and a corona balance, all corresponding very nicely with the design shown by Dondi in his treatise. Here are a couple of examples of similar monastery alarum clocks. Basically, an alarm clock that can be set to wake the warden of the monastery so that he can then go and ring the main bell in the tower. These small clocks would have been mounted on the wall or on a shelf in the warden's cell. In 1953, the Science Museum in London announced an informal exhibition of clocks of the 15th and 16th centuries, and they were inviting people to bring along any example of a clock of this period or before. In the advertisement, they showed the picture of a clock with the corona balance and a toothed dial wheel. And at the bottom of their advertisement, they said that this monastic clock was to be included in the exhibition by courtesy of the Science Museum. In other words, it was a clock that the museum already had within their collection. This advertisement inspired me to do some further searching. I was most interested in having a look at this very early clock. And in the research, I was able to find quite a few pictures and references, text about this particular clock, and some very good black and white photos. And here we can see much greater detail, the layout and the construction of this early Corona balance clock. You'll note that it says that this clock is early 15th century and is the only example of this prototype wheel clock, which must have been made and widespread throughout Europe in the 13th and to the 15th centuries. I was getting more and more interested in this particular clock. Then I found colour photos, which were much more informative because they showed me which components are made of brass and which are made of iron. And here again it says this clock has been traced back to the end of the 14th century in Italy and is the oldest example of a small mechanical clock. But that was as of 1953. Text accompanying the pictures stated that the clock was 10 inches tall, 25 centimeters, and that brings the whole clock into perspective, particularly when you consider that this clock would have been installed in the cell of a single monk. An Italian gentleman by the name of Antonio Simoni, a recognized expert on early Italian timepieces, showed that this clock had been modified over time, as most of these old clocks were, and the original stellate hand had been moved from the center of the dial down onto the alarm work. His drawing on the right hand side of this page shows what he considered was the original layout and design of the clock. In support of this claim, there are many examples still in existence in timber paneling and in drawings showing the stellate hand in the center of the dial. In fact, back in the slide of St. Augustine, the clock in his study has a stellate hand. And you can see also that the dial is 24 hours and has teeth on the outside, so it becomes a rotating disc, and the stellate hand remains fixed in its position. This is a beautifully preserved example of the first mechanical clockwork. It's unique and historically significant, and I consider it a must for any lantern clock collection. Italian lantern clocks offer the complete range of innovation in early clockwork, and this is my collection of Italian lantern clocks, and I believe it's reasonable enough that I should have that first mechanical Italian alarum in this collection. However, it's most unlikely that I would ever be able to obtain the clock that's in the Science Museum in London. The only alternative I have is to actually construct an exact replica. So here I go. The clock being 10 inches or 25 centimeters tall fits beautifully onto an A4 page, and my pictures that I was able to obtain, I was able then to print to full size and use that then to begin the construction of the base and the frame for a replica clock. In my construction, I determined that I would use all of the same techniques. Pinned joints, I would use exactly the same metal where it was used on the original. I would use brass where brass was used. I would use iron where iron was used. I would go as close as I could possibly go to making it exactly the same. The bell I used was cast iron, not brass, not bell metal, but a genuine small cast iron bell. You note the shape is just a simple dome because the bell shapes had not yet been developed any further than a basic dome. Amongst the information I was able to find about this alarum clock was the wheel count, of vital importance to me, when from the dimensions drawing I would be able to create the sizes. From the wheel count I could now create the wheel train in exactly the same way as it was made originally. Using my full-size pictures, I was able to dimension off those based on the 25 centimeter tall frame. So the first thing I started to do was to create the great wheel and the winding drum at the bottom of the time train. Here I've created the first arbor. Carries the great wheel and the winding drum. It's dimensioned and ready machined to take the components that will mount onto this arbor. The great wheel and the click wheel are permanently fixed onto the arbor. With full-size pictures of this mechanism, front, back and both sides, it was a very simple process to transfer dimensions from the pictures to the metal. And here I've created the winding drum and the first arbor components. As each component was completed, it was given its final finish, and in all of the pieces of this clock I was aiming for a satin grained finish, not polished, but a satin finish on every part. To couple the drive from the cable drum to the great wheel via the click work, a click was required, and here the blued iron click has been fitted to the end of the barrel so that it will lock and drive the great wheel. The next arbor up from the great wheel is the first wheel arbor, and here it is in place between the back plate and a potence for a small extension from the front plate to carry that end of the arbor. The significance of that little potence will become visible in the future. If you look closely at the wheels in the original clock, you will note that the crossings out, or the fretting out of the center of the wheel, is not just straight spokes. They are beautifully worked in representation of Gothic style. And so my first wheel had to be a match in size, tooth count and style and design. And here is my drafting for the first wheel. The wheel has been cut and the holes drilled ready for me to put my jeweler's saw blade through there, then fret out the center of the wheel in accordance with my design. Then the wheel was mounted onto its arbor and it's shown in position in mesh with the great wheel. Upward again to the second wheel, which in this case is the escape wheel arbor and pinion. And here the arbor is beautifully tapered to match the original and is positioned between the back plate, and again this wheel has a potence extension off the front plate. Note though that this potence is made of much lighter material so that it can be adjusted. The original wheel count dictated that the escape wheel here, a contrate wheel, had 15 teeth. These were cut and then hand formed to the final shape, and then the centre of the wheel was again crossed out in the Gothic style. Progress so far, shown here in contrast with the picture of the original clock, and I think it's starting to look very close. Rising vertically across the centre of the contrate escape wheel is the pallet staff, and on the left you can see the two pallets that I've inserted to the staff, and they will engage with teeth on opposite sides of the escape wheel. The significance of the adjustable potence now comes into play, as the escape wheel can be adjusted up, down, in and out to give me the correct depthing and operation of the teeth onto the pallets. With creations like this, one gets to a point excitedly where you can apply finger pressure and watch things happen. Exactly here, I was able to blue tack a piece of rod across the top of my vertical pallet staff, apply finger pressure to the great wheel at the bottom of the movement, and watch that top bar oscillate. And that is a really great moment in the creation of anything like this. This was one of the components of this clock that I was really looking forward to making, the corona. Based on the design from the pictures, I created a paper template. I then fitted that paper template to a brass strip of the correct length and breadth, pop marked every change in direction of my paper template onto the brass, and blued the sections that I wanted to cut out. I did not want to cut out the wrong piece at this point of the project. Surprisingly, the task was so simple. One would think this would take hours to thread out, but by sitting the brass strip into the jaws of the vise, it took 20 seconds to do two vertical cuts and then the horizontal cut for each segment to be removed. And here was a trick. To roll this up into a true circle, I simply laid the brass strip on a layer of felt and rolled it with a steel rod. It started to curve up. By increasing the layers of felt, it continued to roll up until ultimately it became a complete ring. Positioned on the ceramic block and held into shape with ceramic pins, the joint was completed with silver solder. So, here is my cleaned corona sitting on top of the pallet staff. To complete the balance, a cross arm was inserted. It was curved at the center to give clearance to the suspension post when it was oscillating. The entire corona was poised, and the sliding weights are fitted to the cross arm to give rate adjustment by moving them in and out towards and away from the center of the balance. Here are some interesting facts about the early control of these alarms. There was no restoring force applied to the balance. For instance, there was no gravity to bring the pendulum back to center. There was no balance spring to bring the balance back to center. These balances operated without any restoring force at all, and that leads to the situation outlined here. In later clocks, the wheel train layout centered around the main arbor of the clock, which led out through the front plate to the dial and carried the minute hand. There the power fed to the center arbor. The regulator, i.e. the pendulum or the balance, controlled the rate at which that power was dispensed, and that was displayed at the dial. So the regulator was truly performing its function as controlling the display and the power. But in these early clocks, the power is at the center of the system, and it controls the display and the regulator. The more weight you add to the clock, the faster it will go. Take weight off, it will slow down, totally at odds to control of timekeeping. Moving on to another of the decorative and functional components of this beautiful clock, the dial wheel, crossed out in true Gothic style with Roman numerals punched into the original cast plate. To replicate this, I laid out the design first on brass plate, cut a rough 100mm disc, fitted a boss to the center, and then proceeded for tooth cutting. The 100mm diameter disc just fitted into my milling machine, and I cut the 72 slots around the 100mm disc in preparation for hand filing of every tooth, as was performed on the original wheel. At the same time, I marked out the indexing holes for the alarm, and there is one hole for every half hour on the 24-hour dial. A somewhat tedious job, but the results are so gratifying when you consider that all this was done by hand, and even the pop marks on each tooth are there still to indicate where a tooth had to be created. The drive for this 72 tooth dial wheel comes from the end of the great wheel arbor. The pinion is 3 teeth, and it's hand filed into the round rod at the end of the arbor. So the end of the great wheel arbor will extend through the front plate and drive the dial wheel. And here, having created the wheel teeth and the 3-tooth pinion, I'm depthing them so that I know the centers for both of these wheels, and I'll be able to transfer that to the frame and mount the dial wheel correctly in correct mesh with the pinion. At this point, mechanically, the timepiece is complete. The capstan is one of the oldest devices used to provide mechanical advantage and move loads, and it was utilized in these early clocks to raise the weight. In this slide, you can see that I have fitted the capstan winding bars to the winding drum. They will be, or can be, used to wind the cable up. The stationary stellate hand was copied from the original, a paper template transferred to brass plate. The design was popped into the brass, ready for fretting. The hand was then fretted out using a jeweler's saw, and here you can see tracing around the design to produce the cutout hand. To complete the hand, It was contoured and fettled to give it a three-dimensional appearance. It was bronzed in relief and then fitted to the dial post, and it remains in a stationary position whilst the dial rotates behind it. As a test for the size and position of the Roman numerals, I created a dial on Corel Draw using water slide film paper. I cut out the circle, soaked it in water, and transferred the transparent film onto the brass dial plate. The Roman numeral font on the original dial could not be found in any font database. It did not exist. It was a true original medieval font. The only way to reproduce this was to actually create the font in the computer using CAD and then milling from that software to create an exact replica of that font size, shape and style. Here you can see the final milled Roman numerals. They are really beautifully done, but they do lack the individuality of a hand done, probably hand stamped numerals. Nevertheless, it's a font that doesn't exist anywhere else, and the numerals were infilled with Liquitex carbon black acrylic ink, a really good substitute for black wax. Having completed the time train, I now move on to the alarm train, and the first component to be made is the winding arbor. And in accordance with the original, it is a hexagonal brass bar with the wheel at one end and a winding crank at the other, pivoting in an iron front mounted bush. The alarm escape wheel or rattler wheel was crossed out, again in the Gothic style, and mounted onto the hex arbor. Here the little front iron mounting is made and mounted onto the base of the clock, and the arbor will run in that as the front pivot. The little winding crank was made from brass rod and then fitted into the end of the hex arbor. Once again, the arbor is carried by a potence mounted off the back frame, and the little potence has got an iron bush in accordance with the original, so that we do have dissimilar metals. Brass arbor running in an iron bush front and back. The alarm lever, made from iron, mounts below the dial with one end tripped by a pin mounted in the dial wheel and the other with a hook to hold the crank in position. Being weight driven, when the alarm release pin comes around and trips the lever, the crank is released and the weight runs the alarm. As was the case for the time train, the alarm train has a vertical, verge and hammer post. The post crosses the centre of the alarm wheel with two flags operating on opposite sides to give a rattler effect. That rattler oscillates the hammerhead inside the bell and rings the alarm. And here you can see the completed alarm system, from the winding arbor, past the rattler wheel and the verge pallets, up the post, then from that into the bell, and then the crosshead on top of the post to hit the bell on both ends of the hammer. With both time and alarm trains complete, all that remains now was to add some of the decoration that was apparent on the original clock. Being weight driven, the clock needed to be elevated and mounted on the wall. So I took inspiration from a Gothic cathedral window to create the design for a bracket as shown here. The backboard of the bracket was to be made up out of two components: a light oak backboard and a dark oak masked front board. The design was cut out of the front board using a coping saw, stained, and then adhered to the light oak backboard to give depth and contrast to the design. The other little components were made in solid oak and stained dark, ready for full assembly. Here is the completed bracket. So finally, the clock has its mounting. It sits beautifully in contrast with the Gothic bracket. 620 years between them. I've done my very best in recreating the original clock using the same techniques, the same materials, the same size, in order to be able to understand a little more about how such a clock could have been made that long time ago.